My OneNote looks weird now. Okay. I just want to add a page. How do I? For heaven's sake. Okay, now we'll get started. So we talked about consistency last time. So that extra sheet of problems that I gave you, let's look at number 11-29. So the 11-29 asks you to show, or we're going to let capital B be a binomial random variable with n trials and probability of success p, and it wants you to show that B over n is a consistent estimator for P. So to be consistent, remember, it has to be unbiased, and basically the more trials you take, the larger the n gets, the closer and closer the estimator gets to the actual parameter. So what we mean by that is, so there's two things that we need to show. One, we need to show that B over n is an unbiased estimator. For P. And two, we need to show that the limit as n goes to infinity of the probability that the absolute value of B over n minus P is less than epsilon is equal to 1 for any epsilon greater than 0. So just to go through the math speak again about what we need for consistent. All right, so this epsilon being greater than 0 just means that think of epsilon as, I like to think of epsilon as a challenge. I want my B over n to be as close as I'd ever want to the P. Okay? So epsilon's a challenge. I challenge you to get the estimator to within this range of the true value. Okay? What this statement says is that no matter what challenge you give me, I can find an n big enough so that I'm relatively certain that I'm that close. And if you've had stats before, you've done confidence intervals, right? Where you say, I am 95%, and we've done confidence intervals in here. I am 95% confident that the mean is between these two values. That's the idea. You're given a challenge, the other way around is getting that margin of error piece and trying to figure out the sample size. But that's that 95% confidence is a probability statement. Right? When we do confidence intervals, before we actually select confidence intervals, we know that 95 or 98 or 99 or whatever our confidence level is, we know that that percentage of all the confidence intervals will contain the true parameter. If you want to make sure that you're within a certain value, then you need to make sure your n is big enough. And you see those kind of things for margins of errors, for polls, and so forth. So that's all that last statement is saying is, no matter how close we want to get, I can take my n big enough and be relatively certain that we get there. It's just a lot of math speak for that. Okay? All right. So that second statement, we're not going to show this directly in general. What we're going to do instead is what we'll show is that we'll show one, that the expected value of B over N really is P, and we'll show that the limit as N goes to infinity of the variance of B over N is equal to 0. We haven't proven this statement yet. We'll prove it here in a minute. But we can prove that if the variance, if it's consistent, then the variance goes to 0, essentially. So we can verify being not consistent if it doesn't go to 0. So we'll verify that it's consistent by showing that the variance goes to 0. Because if we can take it big enough to make the variance be negligible, then the probability that you're going to be far away from the actual value is going to be very, very small, right? Because that's a central limit theorem idea. If I show that it's unbiased, right? If it's unbiased, then we know that over and over and over again, if we do if we do trials over and over and over again, we'll be close to the p. If the variance is small, then I know that I can take n big enough, this will be close to a normal, and the probability that you'll be outside of 3 standard deviations will be small if your n is big enough. Okay? So if we can show that the variance goes to 0, it'll be consistent. Okay? So this is not a difficult thing to do. If I want the expected value of B over N, what can I do with the N? And pull it out in front. And then what variable was B? Binomial. So it was binomial with n trials and probability of success P. So what's the mean of that distribution? NP, and those your n's cancel and you just get P. So this shows that B over N is in fact unbiased. So we still need to show that the variance goes to 0, but we'll do it in the same way that we just did for this one. So now we'll do the variance of B over N. What can we do with the over N piece again? Pull it out, and then when you pull it out, it becomes squared. And then again, B is binomial, so what's its variance? Okay. So we get P times 1 minus P over N. That should look familiar for confidence intervals for proportions. Right? That's our standard deviation, isn't it? Or square root of that's our standard deviation. So if we do the limit now as n goes to infinity of the variance, well, P is a fixed parameter, so as n gets large, what does that limit go to? 0. Good. Which was what we wanted. So that tells us that it's a consistent estimator for P.
So that part was the second part?
That was the second part. Yep, that was part 2. First part was showing it was unbiased. Second part was showing that it's consistent.
So where does that probability of the absolute value of B over N minus P come from?
It's the variance guarantees us that we get that.
Okay. So
That's what we haven't proved that yet. We're going to prove that here in a second.
So if the variance equals 0,
If the limit of the variance goes to 0, then it is consistent.
Shows that second part.
Yeah, that's how it shows the second part, right? We need to prove that theorem, but I wanted to do it first to just show you how you would establish it, and then I'll prove the theorem. It's a good question, though. How did that show part 2? Well, by the theorem that we're going to do here in a second. All right. So let's do that theorem. Oops. So the theorem says that we'll let x1, x2, xn be a random sample from a random variable x. And we'll let theta hat be some function of the random sample. And we'll make it an unbiased estimator. For theta. Then, if the limit as n goes to infinity of the variance of theta hat is equal to 0, then theta hat is a consistent estimator for theta. By the way, I'm using this notation for basically calculating a statistic based on the x1 out to xn. So think of it, probably the simplest thing you do is take the mean, right? So the mean would be an example of a function of the random sample, right? So in that case, u of the x1 out to xn would just be add the x's and divide by n. That would be the function. But that's not our only statistic that we know that we can compute, but that's probably the first one that we do compute, right, is the sample mean. Add them up, divide by how many there are. All right, so let's do a proof. We proved Chebyshev's theorem last time. Remember, Chebyshev's theorem says that we said that the probability that the random variable minus the mean, the absolute value of that is less than a certain number of standard deviations, is less than 1 over the k squared, right? Well, in this case, we're using the theta hat to estimate theta. So the expected value of theta hat is theta, right? So we want to show, or by Chebyshev's inequality, we know that the probability that the absolute value of theta hat minus theta is less than or equal to k times the standard deviation for theta hat, because that's my variable now, will be greater than or equal to 1 minus 1 over the k squared. We're just using theta hat in the place for x here. That's all we're doing. Okay. So this is what we're going to use for our conversion over to becoming a consistent estimator. So, because now by Chebyshev's inequality, we have a probability statement about the difference between theta hat and theta, right? And notice what we essentially want to do is make the k get bigger, right? If we make the k get bigger, then the 1 over 1 minus k squared gets bigger. So that probability is going to have to be 1 if we can make the k big enough based on the n, right? And that's the idea here. Okay, so we're going to let our epsilon greater than 0 be given. remember the definition for our consistent estimator says that if the probability that we have theta hat minus theta being less than the epsilon is equal to 1, right? So I need to show that the limit's going to go off to 1 as n gets bigger. So I certainly can pick my k big enough. Choose k large enough. What do I want to choose k large enough to be? Forgot what I wanted to do. Choose k large enough to be, what do I want to do? I want to make sure that this 1 minus k squared gets really, really small. So I don't want to write it that way. Let's scratch that. Sorry. Let's go back to what we talked about last time. I'm confusing myself what I wanted to do here. Remember last time that we replaced this with an epsilon? Right? If this is I basically want this to be epsilon, right? Right? Okay. So if I'm looking at the probability that we have absolute value of theta hat minus theta is less than or equal to epsilon. Well, I did this last time and screwed it up the first time, so let's see if I can do it right this time. I want to keep it as epsilon. I can write that as what? I want to introduce the standard deviation, but then I would need to divide out by the standard deviation to keep it equal. Right? All I did was just multiply and divide by the sigma. Do you agree? So now what's playing the role of k? In that, the way I have it written is, what's playing the role of k? I've got it flipped. I think it's this piece here, right? That's playing the role of the k. So this should be greater than or equal to 1 minus 1 over epsilon over sigma squared. So this will be 1 minus what? Sigma squared over epsilon squared. Do we agree with that? Okay. So let me rewrite this a little bit. I'm going to rewrite it in the other order. I've got 1 minus oops, I forgot my hat. It's going to go outside and catch cold. I did that for Haley's reaction, specifically for hers, because I know she hates it. Let me write it this way. We certainly have the first inequality from Chebyshev's inequality, right? We just derived that one. I just flipped it the other way around. The second inequality is simply a statement about probability. Probability cannot get any bigger than 1. Right? Do you agree? Okay. Now let's just take the limit as n goes to infinity. That makes the inside piece look like exactly what we want to take the limit of. Well, the limit on the right-hand side is easy. I hope it's easy. What's that limit? 1, right? We agree? we have this. And now on the left-hand side, the only piece I have to worry about taking a limit of course, is this, right? 1's a constant. Epsilon's a given constant. All I have to worry about is this. But that's just the variance. And what are we assuming about the variance as n goes to infinity? Going to 0, right? So this limit's also going to be 1. And what theorem am I using from Calc 1 right now? Squeeze theorem, right? This is squeeze theorem, isn't it? I'm squeezing it in between two limits. Right? The limit in the middle has to be between the two other limits, and they're both 1. So therefore, by the squeeze theorem here, the limit as n goes to infinity of this has to be 1. Therefore, theta hat is consistent. Monday, whatever day that was, we argued that the sample mean was a consistent estimator. We showed directly that the probability went to 0. But we also noticed that remember the variance of the sample mean is equal to the variance of the population divided by the sample size. Right? So your sample mean has a variance that goes to 0 as the n gets large. So you could also use this theorem. We showed it directly last time, but you could also use this theorem to show that the sample mean is a consistent estimator. And again, the whole idea of what we want from consistency is that we want to make sure that if we take the sample size large enough, we are relatively certain that the estimator we're using is close to the value. That's the idea. Whatever we mean by relatively close, that's the margin of error piece. If it's a consistent estimator, I know that I can go get a big enough sample size to be within whatever margin of error you ask for. That's the idea. So yesterday we talked, Monday we talked about, I see too many of you every day. Monday we talked about the sample mean being consistent, which makes sense. Today we just showed that the binomial proportion, the sample proportion, is a consistent estimator. Okay? So another thing that we want to be able to say about estimators, besides being consistent, is whether or not they're efficient. So, as a definition here, let's let theta 1 and theta 2 be unbiased estimators of theta. Then we say theta 1 is relatively more efficient than theta 2 hat if the variance of theta 1 is less than the variance of theta 2. And then the relative efficiency of theta 1 and theta 2 is just the quotient of these things. So you can see that if this quotient is less than 1, then theta 1 hat is more efficient than theta 2 hat. And if it's, if it's less than 1, theta 1 is more efficient than theta 2. If it's greater than 1, then theta 2 is more efficient than theta 1. Okay. So to do an example here of this, let's let x be uniform on 0 to theta. Yes? There is a way to measure the best possible efficiency, and we're going to talk about that next, after I do this example. You're one step ahead of me, Kelly. It's a very good question. Yeah, in general, we talk about efficiency in terms of one estimator versus another. But there is, for any given estimator, there is a best possible case for the variance, and that would be the most efficient estimator. And we'll talk about what that is here in a minute. All right, but let's do this example first. So let's let x be uniform on the interval from 0 to theta. Then we can use two unbiased estimators here. So let's let theta 1 hat be n plus, what do I want to use? I need to use n plus 1 over n times the maximum of x1, x2 out to xn. And theta 2 equal 2 times the sample mean. You can show that both of these are unbiased. Theta 2 is easy to show that it's unbiased. If I'm uniform on 0 to theta, what's my mean? Theta over 2, right? So if I do 2 times the sample mean, the expected value of that will be theta, right? So showing this one is unbiased is not hard. The mean of the distribution is theta over 2, so the mean of the sample means will be theta over 2, so the expected value of 2 times the sample mean is theta. Okay, so that one's not hard. This one requires, of course, a little bit more work. It might be helpful to remember that when you want to do the PDF for the maximum, will be n times 1 over theta times x over theta to the n minus 1. For this particular problem. Remember how we had to do maximum, just to remind you? Do it on the board here. We go back to doing the cumulative distribution function and then taking the derivative. So if I want the maximum to be less than a specific value, then what has to be true about all of the values? If the maximum is less than a number, then all of them had to be less than, right? Right? And then if we're doing a random sample, it's all independent, right? So I need x1 less than x, and x2 less than x, and x3 less than x, so I can just multiply to get those probabilities. And since it's a random sample, all of them can be thought of as coming from the same distribution. So this will just be the probability that an individual one is less than or equal to x to the nth power, right? Just multiply them all together. But this is just a statement about the CDF. So this is the capital F of x to the nth power. where f of x is the CDF of x. I should have called this a y, but that doesn't matter. Now I have the CDF for my maximum. How do I find the PDF? Take the derivative, right? So little g of x by chain rule will be n capital F of x to the n minus 1 times little f of x. So I have to do the derivative of the inside by the chain rule. Okay. So now if we look at the individual pieces here for what I wrote, 1 over theta is the PDF for 0 to theta. X over theta is the CDF from 0 to theta. So it's just a special case of this particular general formula. Remember doing that? It's been a while, but we did that. And what you can do, in this case, you can show that the expected value, if you go through just the maximum, the expected value will be n over n plus 1 times theta, which is why we have to do the n plus 1 over n to get it to be unbiased. You can also show that the variance of theta 1 will be, I don't remember it off the top of my head, it's when I'm looking at this other book, n over n plus 2 times n plus 1 theta squared. The other one's easy. The variance of 2x bar.
That's just a regular theta squared.
This is the regular theta squared, yeah. Because it's in terms of the original parameter. The variance of 2x bar will be 4 times the variance of x bar, right? I agree with that. Okay. That's going to be 4 times the variance of theta, of x over n. But in terms of theta, the variance of x is theta squared over 12. Remember, for the uniform, it's b minus a quantity squared over 12 is the variance. So this becomes theta squared over 3n. So now if we want the relative efficiency, we'll have n over n plus 2 times, oops, I forgot my n plus 1. This is n plus 1 on bottom here is squared. Notice that your oh shoot, I did that wrong. This variance is not right. I've got the variance for just the maximum. I don't have the variance for the other part. This needs to be times, my apologies. This needs to be multiplied by an n plus 1 over n squared.
Why is it squared?
Because what this value is here, the variance of the maximum. What's that? Yeah, the variance of the maximum is that first part.
But for the n plus 1 over n, you just pulled out.
So then what we were doing, the n plus 1 over n times the max. So when we pull it out, it becomes squared. Okay. Sorry about that. I forgot about that part. So this makes this top part of this fraction go away. It becomes a 1. And then we get an n plus 2 times an n in the denominator. And then notice also that your theta squareds will cancel. So this becomes then 3 over n plus 2. So there's our relative efficiency for theta 1 hat and theta 2 hat. So which one's more efficient? Of the two estimators, which one's more efficient? Is that ratio less than 1 or greater than 1? Well, just in general, for any n, as long as n's bigger than 1, as long as you're actually taking a sample size that's bigger than 1, it's going to be less than 1, right? As long as your sample size is bigger than 1, that'll be less than 1. So which one's more efficient? Theta 1, right? Theta 1 hat is more efficient. So since 3 over n plus 2 is less than 1, for n greater than or equal to 2, theta 1 hat is relatively more efficient than theta 2. Okay. So just because theta 1 is more efficient than theta 2, and basically what we mean by more efficient means that you can get a closer guaranteed, well, a relatively guaranteed estimate by taking less of a sample, right? To get that theta 2 to be within a certain margin of error would require more of a sample size than theta 1 would. That's the idea, okay? So more efficient estimators make your sample size smaller for what you'd actually have to sample to get a reasonable estimate for the population parameter. Okay? And that makes sense, right? The smaller the variance, the less likely you are to be away from your mean when you select the sample. Or whatever you're doing, not necessarily the mean. Okay. So the question becomes then, is there a best case scenario? Is there what's referred to as a minimum variance unbiased estimator? Which we will abbreviate MVUE. So to get to that point, we need a little bit of background. So remember we did the likelihood function where we just we had the random sample and we multiplied those things together. That's how we got maximum likelihood estimators. Remember that likelihood function that we had? Okay. All right, so what we're going to do is we're going to let y be the derivative with respect to theta of the log of basically this likelihood function idea, but the log of the PDF in this fashion. Okay. I know it looks odd, but it has some properties that we want. All right. So we did this before with likelihoods and stuff, where we took the log of it to help us be able to change the products into the sums, those kind of things. Same concept here. What we notice, though, is that when we actually do the derivative, of course, the derivative will be 1 over the inside times the derivative of the inside piece, correct? In general, we notice that if we wanted to take the derivative of this inside part, it's just this partial times itself. That helps us with the following. If we want the expected value of y, doesn't matter if we have a discrete or a continuous distribution here. I'm going to use continuous just because I'm going to write it in terms of an integral rather than a sum. If I want the expected value of y, this would want to be this would tell us to do the y then times the PDF. That's how we do expected value, right? We agree with that? That's how we do expected value. You take the function times the PDF. All right. Well, let's think about this. If I integrate the PDF over the entire sample space, or again, we could change this with sums, what do we have to get? 1, right? So now if I differentiate both sides with respect to theta, what's the right-hand side become? What is the derivative of 1 with respect to theta? 0, right? We agree with that? Yeah? Now what I really would like to do is move this inside here and take the derivative of this thing. In order to be able to do that, I've got to make sure that this interval doesn't contain theta. For example, that last example we did where it was uniform on 0 to theta, the sample space depended on the theta, right? As theta changes, the sample space changed, right? If my interval that I'm integrating over, I know I wrote minus infinity to infinity here, but remember, in general, all we really mean is just the entire sample space. If your sample space depends on theta, then I can't do what I'm about to do, okay? As long as if x is what's referred to as a regular random variable, so the sample space does not depend on theta. So for example, normal distribution would be regular, exponential distribution would be regular, Poisson would be regular, binomial would be regular, right? All of those things are regular. They don't depend on the parameters. The sample space doesn't depend on the parameter. If x is regular, then we can move that partial on the inside. And what we notice about this partial derivative is that this is actually the same thing as this expression. Now the reason why those two things are equal to each other is because, remember when we did, think about what you did back in Calc 1 again. When you had something like x to the x power, you can't differentiate it directly, you have to use logarithmic differentiation. To start your logarithmic differentiation, you take the log of both sides, and then use your chain rule. Right? Wait a minute. Well, yeah, that's true in general. Right? So, what did I want to do here? Need to rearrange it. So this is just true in general, and I would get things to cancel out. But if I just want, so the left-hand side here, if I write it, if I leave it, instead of actually taking the derivative like you would have done in Calc 1, if I literally just say it's the derivative of the log, then I can multiply both sides by f of x, and I have that, don't I? That the derivative of the function is just the derivative of the log of the function times the function. It's just rearranging it. How does that compare up there? We've got derivative of the function, and this is derivative of log of function times function. It's the same thing. It's just logarithmic differentiation written in a really funky form. This left-hand side here is the expected value of that y we started talking about. So going back up here, this was how we defined y. The expected value of that turns out to be 0. Okay? We need that to help us figure out the variance. Remember, we're going to variance stuff, right? We're trying to figure out what the minimum possible variance is for any estimator. Well, to figure out variance, I need expected value. But now this makes it easy because I can figure out variance now just by doing the expected value of the variable squared. Okay? And it's going to turn out that, well, we're not going to do it today because I'm out of time, but it's going to turn out that the variance is actually going to be in terms of the second partial of the log function, which is kind of cool. Because then I can actually figure out the variance just by taking a couple of derivatives. Okay? And then we'll get to the point where we can say the minimum possible variance will be in terms of that second derivative of the partial, or the second partial derivative of the likelihood function. That's where we're headed. As far as your test goes next week, this stuff that I just started talking about, I'm going to stop at relative efficiencies of estimators. So this new stuff that I'm just now starting is not going to be on the test. It'll be on the take-home final, but it won't be on this next test. Next week? Yeah, whenever. Thursday or Friday. Friday you don't have classes because of celebration of scholarship too, so makes it a little bit easier.
Will it be on Excel, some of it?
Yes, some of it will be on Excel because it'll be like your last homework, right? Yeah. Yeah. So, all right. So we'll talk a little bit about that after break. Remember we don't have class Monday? Because I decided not to have class Monday.
We need that.
Yeah, we do not have class Monday, but you have other classes, but we don't have this class Monday. Did I not tell you that I had time?
No, you did.
I did? Okay, I thought I did.
Because I called you a saint, remember?
Yeah, that's right, because I said I don't get that very often.
Here?
Oh, thank you. Yeah, just lay it there. That works. Oh, way down there at the bottom.